February 20th, 2025, Stennis Space Center, Mississippi. NASA fires up the RS-25 engine, 111% power. Combustion chamber temperature of 3,799 degrees Fahrenheit, 5 or 12,000 pounds of thrust. The test is a success. Engineers applaud. But in this moment, NASA is utilizing a fundamental design that is 83 years old, developed in 1942 in Peenemünde, Germany, by German engineers. The turbopump. Every time SpaceX launches a rocket, every time Blue Origin tests, every time NASA prepares for Artemis, they're using the same basic principle, 4,000 revolutions per minute. Centrifugal acceleration, injecting propellant into the combustion chamber under extreme pressure. The physics haven't changed because they're optimal. Today, I'm going to show you the documented engineering lineage from Peenemünde in 1942 to SpaceX in 2025. The story begins with an engineering problem that seemed unsolvable in 1935. Wernher von Braun wanted to build a large rocket, not small like Goddard's experiments, but big, 46 feet tall, 27,500 pounds heavy, with an engine generating 55,000 pounds of thrust. The problem was simple. How do you move enough fuel into the combustion chamber? Fast enough? Technically, the A4 engine, later known as the V-2, needed 33 gallons per second, 75% ethanol, plus liquid oxygen at minus 297 degrees Fahrenheit, in a 60-second burn time. 20,000 pounds of propellant had to be moved. No pressure-fed system could handle that. The tanks would be too heavy. The physics just wouldn't work. In 1935, von Braun sought out pump expertise. He found Klein, Schanzlin and Becker in Frankenthal, KSB, a German company, specializing in centrifugal pumps for industrial plants. But a rocket pump, that was something entirely different. It had to be light, a maximum of 330 pounds. It had to move enormous volumes, 33 gallons per second. It had to withstand extreme temperatures, minus 297 degrees for LOX, plus 752 degrees for the fuel. And it had to separate both fluids from each other, perfectly sealed. KSB developed the centrifugal pumps. 2 separate units, one for ethanol at ambient temperature, one for LOX under cryogenic conditions. But how to power them? An electric motor would be too heavy. Von Braun contacted Helmuth Walter, an engineer in Kiel. A specialist in concentrated hydrogen peroxide, Walter developed an ingenious solution, a steam turbine, powered by the catalytic decomposition of high-test peroxide. The turbine was a masterpiece of German metallurgy. It had to withstand 725 degrees Fahrenheit, high-pressure steam. It had to rotate at 4,000 revolutions per minute, stable, without vibration, without failure. And it had to do it all in a 330-pound package. The KSB Walter turbopump was the first of its kind in the world. No other nation had anything comparable. Let's take a closer look at the technical specifications. The LOX pump. Centrifugal design with 18 blades, each blade precisely calculated for maximum efficiency. The inlet was 3.15 inches in diameter, the outlet 1.57 inches. That created enormous pressure, from ambient pressure to 220 psi in the combustion chamber, at minus 297 degrees Fahrenheit. The LOX had to remain liquid. Any heat leakage would vaporize it. Catastrophic failure. KSB solved this with special seals, graphite impregnated, asbestos-free. The shaft ran in ball bearings, hardened for cryogenic conditions. The tolerances were extreme, 0.002 inches maximum. At 4,000 revolutions per minute, any imbalance would create catastrophic vibration. The Germans had the precision. In 1942, the ethanol pump had different challenges. Room temperature. Easier thermally, but higher volume. 128 pounds per second of ethanol versus 148 pounds of LOX. The pump was larger, 24 blades, throughput of 33 gallons per second. The drive pressure came from the Walter steam generator. Helmuth Walter's steam generator was geniusly simple. High-test peroxide, 80% concentrated hydrogen peroxide, dripped over a potassium permanganate catalyst bed. Instantaneous decomposition. 2H2O2 becomes 2H2O plus O2. Exothermic reaction. At 25 degrees Fahrenheit steam at 435 psi pressure. This steam powered a two-stage turbine. First stage for LOX pump, second stage for ethanol pump, mechanically coupled on a single shaft. The entire turbopump assembly weighed 328 pounds. By modern standards, that's heavy, but in 1942, revolutionary. American engineers tried to analyze the V-2 turbopump in 1946 at Aberdeen Proving Ground. They disassembled a complete unit. Their reports showed a maze, the precision, the materials, the integration. It was 5 to 10 years ahead of its time, but the turbopump alone didn't solve the thermal problem. 4,900 degrees Fahrenheit in the combustion chamber. No metal alloy of the 1940s could withstand that, not for longer than seconds. The V-2 needed a 60-second burn time, at least. This is where Walter Thiel came into play. Thiel was chief engine engineer in Peenemünde, 34 years old in 1942, an absolute specialist in rocket engines. He developed a system that every rocket uses today, regenerative cooling. The principle was elegant. The 75% ethanol fuel entered near the nozzle opening via 6 pipes. It flowed through a double-walled construction, all the way up the nozzle to the combustion chamber tip. In doing so, the fuel absorbed the extreme heat. It was preheated, more efficient, and the combustion chamber wall remained below a critical temperature. The technical details were impressive. 1,247 cooling channels in the V-2 combustion chamber, each channel precisely dimensioned. Ethanol flowed at 33 gallons per second. It absorbed heat at 4,900 degrees. The wall temperature stayed below 1,472 degrees, just enough for the chromium-vanadium steel alloy to survive. Without Thiel's regenerative cooling, the V-2 would have been impossible. October 3rd, 1942, Peenemünde, test number 4. The V-2 stood upright on the launch pad, 46 feet tall, 27,500 pounds heavy, Wernher von Braun observed. Walter Thiel checked the combustion chamber one last time. The KSB Walter turbopump whirred, 4,000 revolutions per minute. High-test peroxide decomposed catalytically. 725-degree steam powered the turbine. The centrifugal pumps accelerated. Ethanol and LOX flowed, 33 gallons per second. Ignition. The combustion chamber exploded in flames, 4,900 degrees Fahrenheit. 55,000 pounds of thrust. The rocket lifted off, slowly at first, then faster. The turbopump worked perfectly. Regenerative cooling functioned, 60-second burn time. The V-2 reached 53 miles in altitude, 300 miles per hour. It broke the sound barrier. It reached the edge of space. For the first time in human history, von Braun later said, that was the moment when space became accessible. But technically, it was the moment when the turbopump proved that large rockets could work. Without the turbopump, no Saturn V, no space shuttle, no SpaceX, nothing like it. The Allies in 1942 had nothing comparable. America had Goddard, a brilliant inventor, but his biggest rocket, a mere 15 feet tall, maximum altitude 1.6 miles. No turbopump system. Pressurized gas feed. Primitive by comparison. The Soviets had Katyusha, solid fuel rockets, artillery. No liquid fuel technology. Great Britain was experimenting with small rockets, nothing over 10 feet long. The V-2 turbopump was 10 years ahead, minimum. But the Allies wouldn't know that until March of 1945. Operation Crossbow. British intelligence photographs revealed Peenemünde, huge rockets, launch pads, production facilities. Churchill authorized bombing raids, August 17, 1943. 596 Lancaster bombers. Peenemünde was hit. Walter Thiel died in that attack. 49 years old, the man who invented regenerative cooling. But the turbopump technology survived. Production shifted underground. Mittelwerk, Nordhausen, concentration camp, Dora. 60,000 prisoners built V-2 rockets. 5,975 units between 1944 and 1945, each with a KSB Walter turbopump, each with Thiel's regenerative cooling. The rockets flew against London, Antwerp, Liège. 3,000 people died. But technically, they demonstrated something that would change the world. March 1945, Operation Lusty. Allied troops advanced through Germany. Special teams searched for German technology. CIOS, Combined Intelligence Objectives Subcommittee, T-Forces, British, American, Soviet, all chasing the same thing. V-2 rockets, production facilities, blueprints, and scientists. March 28, 1945. American troops reached Nordhausen, the underground Mittelwerk. They found 14 complete V-2 rockets, hundreds of turbopumps, combustion chambers, components, tons of technical document. Everything was confiscated. Operation Paperclip began. The Soviets reached Peenemünde in May 1945. Too late. The Americans had Wernher von Braun. They had the best scientists, 127 German rocket scientists. Von Braun negotiated skillfully. He surrendered to the Americans, not the Soviets. He knew what his knowledge was worth. May 16, 1945. Fort Bliss, Texas. Von Braun and his team arrived. With them came the V-2 components from Nordhausen, 100 complete rockets, assembled from parts. The US military wanted to learn. How does the turbopump work? How does regenerative cooling work? How do you build large rockets? The Americans tested V-2 rockets at White Sands, New Mexico. 67 launches between 1946 and 1952. They learned, they copied, they improved. But the fundamental design remained German. The turbopump, the regenerative cooling, the combustion chamber geometry, all came from Thiel and the KSB Walter team. But let me show you just how desperate the Americans were for this technology. Project Hermes, 1946. General Electric was contracted to understand V-2 technology and develop American versions. They had the rockets, they had the parts, they even had German scientists as consultants. But to build their own turbopump, that took years. Technical Report 718, published in 1952, documents every aspect of the V-2 turbopump. 847 pages, detailed drawings, material specifications, test data. The Americans studied every millimeter. Why? Because their own attempts failed. Between 1946 and 1950, General Electric developed 3 different turbopump prototypes. All failed in tests: vibration, seal failure, thermal problems. The breakthrough only came when Wernher von Braun became directly involved. He brought Konrad Dannenberg with him. Konrad had been responsible for turbopump testing at Peenemünde. He knew every detail, every difficulty, every solution. With Dannenberg's direct help, General Electric finally built a working copy. In 1952, 10 years after the Germans first did it, the Soviets had similar problems. Operation Osoaviakim brought 2,200 German specialists to Russia. Helmut Grötrup was among them. He had worked on control systems at Peenemünde. The Soviets forced him to build V-2 copies. Project Vostok, not to be confused with the later spacecraft, Gertrup and his team built the R-1 rocket, an exact V-2 copy, with German turbopumps from Mittelwerk stockpiles. But when they tried to build their own turbopumps, they failed repeatedly. Only in 1950, with the help of German engineers, did they succeed. The R-2 rocket had Soviet-built turbopumps, but the design, German, every aspect, every tolerance. Every material specification copied from KSB Walter Originals, 1950. The Mittelwerk team was relocated to Redstone Arsenal, Alabama. Von Braun got a new project, the Redstone rocket, a medium-range ballistic missile for the US Army. Technically, Redstone was an enlarged V-2, same turbopump philosophy, same regenerative cooling, same propellants, LOX and ethanol. The Germans built America's first operational rocket. But that was just the beginning. The turbopumps got bigger, more powerful, more complex, but the fundamental principle remained. And then came Sputnik, October 4th, 1957, Baikonur Cosmodrome, Kazakhstan. The Soviet Union launches Sputnik 1, the first artificial satellite. America is shocked. Eisenhower asks, how did the Soviets beat us? The answer was ironic. With German technology. The Soviets had reached Peenemünde after the Americans. They found production facilities, parts, documents, and German engineers who didn't go to America. Operation Osoaviakim, October 21st, 1946. 2,200 German specialists were deported to Russia, forcibly, with their families. They built the Soviet R-7 rocket, the rocket that launched Sputnik. Technically, the R-7 was more advanced than the V-2, bigger, more powerful. But the turbopumps, German principle, the regenerative cooling, Thiel's design, the Soviets had learned, just like the Americans, from the Germans. America had to react. January 1958. Wernher von Braun got the green light, Project Mercury, Project Gemini, and then the big one, Project Apollo. John F. Kennedy, May 25, 1961. We choose to go to the moon before the end of the decade. Von Braun became director of the Marshall Space Flight Center. His mission, build the biggest rocket in history. Saturn V, 360 feet tall, 6.5 million pounds fully fueled, 5 F-1 engines in the first stage. Each F-1 generated 5 million pounds of thrust, combined 7.5 million pounds. That was 136 times more than the V-2. But the fundamental technology, German. The F-1 engine was developed by Rocketdyne, an American company. But look at the technical details. Regenerative cooling, like Thiel in 1942. Turbopump driven, like KSB Walter. The F-1 had improvements, of course. The LOX turbopump rotated at 500 revolutions per minute. It generated a whopping 69,000 horsepower. Just for the oxygen pump, the fuel turbopump handling RP1 kerosene cranked out another 45,000 horsepower. That's a combined 114,000 horsepower solely to pump fuel. That's more power than some nuclear power plant turbines. And all of that in a machine weighing less than 2 tons. The turbopump was so powerful that if you used the exhaust directly, it could have generated 7,000 kilograms of thrust. Enough for a small rocket. Just from the exhaust gases alone, let's take a closer look at the F-1 LOX turbopump, the Rocketdyne Mark 10 turbopump. Inlet diameter 254 millimeters, 7 stages of impellers, each stage progressively increasing the pressure from 0.7 bar at the inlet to a massive 62 bar at the outlet. That's an 89-fold pressure increase. The turbine itself was 2-stage, driven by hot gas from the gas generator. RP1 and LOX burned in the gas generator under fuel-rich conditions. creating 730 degrees Celsius exhaust gas. That drove the turbine at a blazing 5,500 revolutions per minute. The precision was extreme. The turbine blades were made from Inconel X750, a nickel-based super alloy. Each blade individually cast and machined. Tolerances were under 0.1 millimeters. At 5,500 RPM and 730 degrees, any imbalance would create catastrophic consequences. Rocketdyne developed special balancing techniques, but the underlying philosophy? German. From KSB Walter in 1942, the kerosene turbopump had a different design, only 2 stages, but a higher mass flow rate, 788 kilograms per second of RP1 kerosene. The outlet pressure was 67 bar. The turbine rotated at 5,900 revolutions per minute, faster than the LOX pump. The power output, a staggering 45,000 horsepower. That's like having 22 Formula One engines combined. The F1 turbopumps had a problem the V2 never did. The thrust was 27 times higher. Vibrations were proportionally worse. Between 1959 and 1963, the F1 engine exploded 14 times during tests, mostly due to turbopump issues, cavitation, resonance, seal failure. The team struggled for 4 long years. They finally solved it with anti-resonance dampers, but the basic principle unchanged: centrifugal turbopump, regenerative cooling, a German invention. But here's what's crucial. The F1 design team had access to all the V2 documents. Technical Report 718 detailed Peenemünde blueprints, and they had Wernher von Braun every single day, consulting, reviewing, problem-solving. The technical lineage is directly documented. V2 turbopump to F1 turbopump. 20 years of development, but the same basic principle. 5,847 cooling channels in the F1. The V2 had 1,247, more channels, better cooling. But the concept? Walter Thiel's regenerative cooling. RP1 kerosene flowed through the double wall. It absorbed heat. It became preheated. The combustion chamber wall stayed cool enough. At a scorching 3,300 degrees Celsius combustion chamber temperature. The same physics, the same engineering. German DNA in America's greatest rocket. July 16, 1969, Kennedy Space Center. Saturn V launches Apollo 11. Neil Armstrong, Buzz Aldrin, Michael Collins. 5 F1 engines ignite, each with a German-inspired turbopump, a perfect 2 minutes and 41 seconds burn time. The first stage carries Apollo to an altitude of 68 kilometers. The rest is history. July 20th, 1969, the Moon. But for Wernher von Braun, this was personal. 27 years earlier, he had tested the V2 in Peenemünde. Now his rocket had carried humans to the Moon. The technology was the same, only bigger, more powerful, but at its core, German. After Apollo came the Space Shuttle. A new design, reusable. But take a look at the RS-25 engine. Also known as the Space Shuttle main engine, Rocketdyne built it, again, liquid hydrogen and oxygen, cryogenic. The turbopumps were masterpieces. The LOX high-pressure turbopump spun at 28,120 revolutions per minute. The hydrogen high-pressure turbopump reached a mind-boggling 37,000 revolutions per minute. That's 7 times faster than a Formula One engine. At cryogenic temperatures, minus 253 degrees Celsius for hydrogen, minus 183 degrees for oxygen. The material science was advanced, superalloys, nickel-based, but the operating principle, centrifugal acceleration, just like KSB in 1940, and the cooling, RS-25 uses regenerative cooling. Liquid hydrogen flows through 1,080 cooling channels in the nozzle. It absorbs extreme heat, a furnace-like 3,315 degrees Celsius combustion chamber temperature. The hydrogen turns into gas. It expands, perfectly preheated for combustion. Thiel's concept, 40 years later. Even more optimized. From 1981 to 2011, the Space Shuttle flew 135 missions. Each mission used 3 RS-25 engines. Each engine had 2 turbopump stages, high pressure and low pressure. Together, they generated enough force to deliver 23 million horsepower. In pumping power, that's the entire electricity production of a small country, just to move fuel, and all of it based on a concept from 1942. Now, 2025, commercial spaceflight. SpaceX dominates. Starship and Super Heavy, powered by Raptor engines. Elon Musk calls Raptor the most advanced rocket engine ever built. Technically, he's right. Raptor uses full-flow staged combustion. Both propellants, methane and oxygen, pass through preburners. This maximizes efficiency, but take a look at the turbopumps. Raptor 2 has 4. 2 for methane, 2 for oxygen. The methane turbopump generates 37 megawatts of power, equivalent to 50,000 horsepower. The LOX turbopump generates 31 megawatts, together 68 megawatts, 91,000 horsepower, just for pumping, in an engine that produces 230 tons of thrust. The rotational speeds are extreme, over 20,000 revolutions per minute, at 330 bar combustion chamber pressure. That's the highest pressure ever achieved in a rocket engine. The materials are modern, additively manufactured, 3D printed from superalloys. The computer control is digital, but the basic principle. Centrifugal turbopump, like KSB Walter in 1942. Let me show you how direct the technical lineage is. The Raptor methane turbopump, 3 stages of impellers, centrifugal design, inlet at 5 bar, outlet at 350 bar, a 70-fold pressure increase, exactly like the V-2, but with much higher pressure. The turbine is powered by methane-rich combustion from the pre-burner, 800 degrees Celsius gas. Drives the turbine at 20,000 RPM. The LOX turbopump is even more extreme. 4 stages, inlet at 1 bar, outlet at 350 bar, cryogenic at minus 183 degrees, exactly the same temperature as V2 LOX. The seals are modern, ceramic-based. But the problem? Identical to 1942, separating liquid LOX at minus 183 degrees from hot gas at 800 degrees. KSB solved that in 1942. SpaceX is solving it in 2025. The same physics. Elon Musk once said, Raptor is the hardest engine ever built. He's right. Full-flow stage combustion is extremely complicated. But the turbopump? That's proven technology, proven for 83 years, from Peenemünde to Boca Chica, V-2 to Starship. The lineage is unbroken. And what about the cooling? Raptor uses regenerative cooling. Liquid methane flows through cooling channels in the combustion chamber. It absorbs heat at a scorching 6,300 degrees Fahrenheit. It becomes gaseous, preheated, more efficient. Thiel's concept, 83 years later, still optimal because the laws of physics don't change. Blue Origin, Jeff Bezos's company, is developing the BE-4 engine, liquid methane and oxygen. Similar to Raptor, the BE-4 generates 540,000 pounds of thrust. The turbopumps spin at 19,000 RPM, generating a combined 70,000 horsepower. Regenerative cooling, centrifugal turbopumps, German technology from 1942, in an engine scheduled to fly in 2025. These technological truths aren't just history, they're in every smartphone. Because satellites launched with these engines make it possible, they're in every airplane. Because jet engines use similar principles, they're in every rocket. If you appreciate this deep dive into engineering, if you want this true story preserved, support this channel with super thanks. It helps tell these forgotten technical truths. Let's summarize the complete technical evolution. Take a look at this progression. 1942, the V-2, KSB Walter turbopump, 4,000 RPM, 33 gallons per second, 1247 cooling channels, regenerative cooling by Walter Thiel. That was year zero for large rockets, combustion chamber pressure, 220 psi, thrust, 25 tons, burn time, 60 seconds. The foundation, every detail was revolutionary. The Germans didn't just invent the turbopump, they invented the entire system: catalytic steam generation for power, cryogenic seals for LOX, precision balancing for high RPMs, double-walled combustion chamber for coolant flow, injector plate with 18 ports for optimal mixing. Every aspect had to be invented from scratch. Between 1936 and 1942, 6 years of total innovation. 1958, Redstone, von Braun's first American rocket, enlarged V-2 turbopump. Same principle, more power. 1969, Saturn V F-1, 5,500 RPM LOX pump, 69,000 horsepower, 5,847 cooling channels. Thiel's concept scaled up. 1981, Space Shuttle RS-25. 37,000 RPM hydrogen pump, 1,080 cooling channels, a cryogenic masterpiece. German principle. 2025, SpaceX Raptor, 20,000 RPM, 68 megawatts of pump power, 4,800 psi combustion chamber pressure, full flow staged combustion. But the turbopump, 83-year-old physics. Blue Origin BE4, 19,000 RPM, 70,000 horsepower, methane oxygen, regenerative cooling, German heritage. The numbers show the evolution, but the fundamental principle is unchanged. Centrifugal acceleration moves propellant. Regenerative cooling protects the combustion chamber. That's physically optimal. There's no better way. With chemical rockets, the Germans found the optimal solution back in 1942. Today, SpaceX launches Starlink satellites. Every week with Raptor engines, NASA is preparing Artemis to go back to the moon with RS-25 engines. Blue Origin is developing New Glenn with BE4 engines. All use turbopumps. All use regenerative cooling. All stand on the shoulders of German engineers. From 1942, February 20th, 2025, we return to where we began. Stennis Space Center. NASA fires an RS-25 engine, 111% power. The test is perfect. The turbopump functions flawlessly. 83 years after Walter Thiel developed the concept. 83 years after KSB built the first centrifugal pump for a rocket. The technical lineage is proven. Peenemünde to SpaceX, V-2 to Raptor. This isn't speculation, this is documented. U.S. Army Technical Report 718, NASA SP-125 Saturn V documents, Rocketdyne F-1 development reports, SpaceX Raptor technical presentations, all show the same truth. The fundamental rocket technology is German from 1942, and it's being used to this day. When you look at the International Space Station, think about V-2 turbopumps. The rockets that launch the ISS modules use this principle. When you use GPS, thank German engineers, the satellites were launched with turbopump-powered rockets. When you see weather forecasts, the same thing. Communication satellites, the same thing. Earth observation, the same thing. The irony is perfect. A weapon developed for destruction became the basis for space exploration. V-2 rockets killed 3,000 people, but V-2 technology took humans to the moon, launched 15,000 satellites, enabled global communication, GPS navigation, weather monitoring, climate research, all because of a turbopump developed in Peenemünde back in 1942. Walter Thiel died in 1943 in a bombing raid. He never saw what his regenerative cooling system made possible. Wernher von Braun saw Apollo 11. He died in 1977. He saw the space shuttle design, but he never saw SpaceX. He never saw commercial spaceflight, private companies, landing and reusing rockets. But he would recognize the turbopumps instantly. The technical evolution is clear. V-2, 25 tons of thrust; Redstone, 35 tons; F-1, 680 tons; RS-25, 232 tons in a vacuum; Raptor 2, 230 tons; BE-4, 240 tons. The numbers increase, but the technology is the same. Centrifugal turbopump, regenerative cooling, German physics, optimized over 83 years. Now you understand why NASA, SpaceX, Blue Origin, ESA, Roscosmos, CNSA all use the same basic design, not because they aren't innovative, but because the Germans in 1942 found the physically optimal solution. You can improve it, make it bigger, faster, more efficient. But you can't surpass the fundamental principle, not with chemical rockets. The next generation is already in development. SpaceX Raptor 3, higher pressure, 5,075 psi, more thrust, 280 tons. But the turbopump, centrifugal, the cooling, regenerative, Blue Origin BE-7, liquid hydrogen, lunar lander engine, turbopump. Regenerative cooling, ESA Prometheus, methane oxygen, reusable, low cost, turbopump, regenerative cooling. 83 years later, the physics remains. The German innovation of 1942 remains the standard. That won't change. Not until we move beyond chemical rockets. Nuclear thermal, maybe, electromagnetic, but for chemical propulsion, KSB Walter turbopump and Walter Thiel regenerative cooling are physically optimal. NASA uses German V-2 turbopump designs from 1942 in modern rockets. SpaceX 2, Blue Origin 2, every spacefaring nation. That's not an opinion. That's documented, technical reality. The lineage is proven. Peenemünde to Stennis Space Center, Walter Thiel to Elon Musk's engineers, 83 years of direct evolution. Is it theft or technical evolution? Is it homage or appropriation? The Germans never got credit. Walter Thiel is almost forgotten. KSB is never mentioned in SpaceX presentations, but the technology lives on in every rocket, every day. Share your thoughts down in the comments section. Was German technology stolen, or was Operation Paperclip a legitimate transfer of knowledge and expertise? Let's get the conversation started. What are your thoughts? Don't hold back. We want to hear your opinions. Dive into the debate. Did the Allies cross a line, or was it a necessary measure in the post-war era?